Thank you very much, Professor Vega, for wonderful introduction. So can you see my screen?
Yes.
Okay, so let me start. So actually, I am the president of AAPPS, which is the Association of Asia Pacific Physical Societies. And we have 18 member societies. And your Physics Society of the Philippines is one of them. And I'm very glad to have a chance to speak here at the conference, the first online conference. Yeah, congratulations on the successful conference. And we have 3 divisions so far: plasma physics, astrophysics, and nuclear physics, and 2 more are coming maybe next year: condensed matter physics divisions and particle physics divisions. So today, I am going to talk on gravitational waves, which is the ripples of the space-time. So when massive bodies like neutron stars or black holes, binary bodies, inspiral each other, yeah, this kind of gravitational waves can be produced, and finally they collide with each other. And after that, you find a quiet universe again. But as you know, gravity is the weakest force among the 4 fundamental interactions. And so gravitational force between a proton and electron is 40 digits smaller than the electric force. What does it mean? So this means that gravitational waves have an extremely high permeability. This means that direct detection of gravitational wave is very, very difficult. But on the other hand, once we can detect it, we can study inside the neutron stars and near horizon events of black holes, as well as the physics of the very early universe, where the photons cannot probe. And we have a number of goals on the gravitational wave physics and astronomy, like in the aspect of fundamental physics, is general relativity of Einstein correct theory of gravity, or does black hole have really no hair? What is about the neutron star equation state? Astrophysics aspect, what about the black hole mass distribution? Or what is the progenitors of the gamma ray burst? In cosmology, can we directly see the early universe just after the Big Bang? And the answer is yes, if we use the gravitational waves. And there are a number of proposed sources of the gravitational waves. Yeah, as I just shown in the movies in the beginning, binary neutron stars or binary black holes are primary candidates of the gravitational wave events, or burst-like events associated with supernovae or cosmic string bursts are also one of the candidates. And pulsar rotation emits a continuous sources, or in the early universe during the inflationary era, quantum mechanically generated gravitational waves produces a stochastic background. All of them will bring us about a very interesting physics once we can detect them. And by nature, gravitational waves is a transverse waves like photon, but with 2 polarizations, and plus mode and cross mode like this. And so if gravitational wave comes from the heaven and penetrating the earth, so our land will be somehow squeezed like this. But these are, of course, exaggerations of many, many digits. And only we can experience only tiny, tiny ripples of the fluctuation of the space as well as time. And how weak is it? So because it's so weak, we can treat the gravitational waves as a small perturbation around the Minkowski spacetime. And this Hij denotes the amplitude and propagation of gravitational waves. And once you can find the sources like binary stars or neutron stars, and you can calculate the quadratic moment tensor of this system. And if you take 2 time derivatives, it will give you the Hij signal. And this is inversely proportional to the distance between the sources and observers. And for example, if 2 identical neutron stars with 1.4 solar mass, which is more or less typical mass of a neutron star, at a distance of 1 megaparsec, which is equal to 3.24 million light year, then the typical amplitude of the resultant gravitational wave is only 3 times 10 to minus 21. And the relative shift of the distance, as shown in the exaggerated picture in the previous view graph, is just delta L over L of order of this quantity. And we can still measure such a tiny displacement with a sophisticated technique of the kilometer scale laser interferometer. So you install a high intensity laser from here and split their beams into X direction and Y direction. And on each end, we have 2 mirrors, and lasers goes back and forth many times to form a Fabry-Perot cavity, and finally returns to here and to the photon detectors. And the lasers flying this direction also come back here, and they make interference patterns once gravitational wave propagates through this laser interferometer. Because the distance has a tiny difference between x-axis and y-axis. And nowadays there are 4 worldwide detectors worldwide of the kilometer scale laser interferometers. 2 are in United States. Both have a 4-kilometer arm length. The third one exists in Italy near the Pisa, and it has a 3-kilometer arm length. And in Japan, we have constructed a Kagura interferometer deep underground near Super Kamiokande. It also has a 3-kilometer arm length. And now this HIJ, or gravitational waves, square amplitude of expectation value of gravitational waves, can be Fourier decomposed like this. And h of f, or square root of this quantity, gives a strain in Fourier space. And because of this Fourier frequency integral, h of f has a unit 1 over square root of hertz. And gravitational wave detectors suffer from a number of different sources of noises. And noises can also be measured in the same units, like this. And these are the typical noise curves of the initial LIGO and advanced LIGO current one and future Einstein telescope. So all of them have a maximum sensitivity around 100 hertz band. And at higher frequency, the noise is dominated by shot noise of lasers. And at lower frequency, here thermal noise of the mirrors dominates. And at the lowest frequency, seismic noise is the dominant source of the noises. And anyway, once we reach at a level of 10 to minus 22 or 23, we can measure the gravitational waves. And as you may remember, this first happened on September 14th of 2015, and it was announced several months later in February 2016. At that time, the LIGO strain noise curve was something like that. And these are the observed signals. This is from Hanford, and that is from Livingstone. And as you can see, both signals coincide, which shows the fact that they are not noises, but they are actual signals of the gravitational waves from the distant universe. And as you may remember, these are the signals from the coalescence of the binary black holes. In the initial in-spiral phase, we have more or less sinusoidal type waves, and we can learn the informations of the distance, masses, direction, and spin of these black holes. And this is a collision phase and can be only studied by numerical relativity. After coalescence, we are left with a single black hole. And this ring down phase gives us information on the mass of the new black hole and its spin. Now, this has been the observation timeline of the advanced LIGO, which started sometime in September 2015. And actually, even before the start of the real observation run, they observed the first event, which is now called 150914, just referring to the date of the event. And second observation period in the next year. And at the later stage of this second O2 period, Virgo detector in Italy joined O2 in August of 2017. And immediately after joining, they have luckily detected the black hole event. And 3 days later, they detected the event from the binary neutron star merger finally. And the third period of the observation started last April, April last year, and still continuing, supposed to be continuing. And Kagura was actually ready to join this O3 early 2020, but at that time, advanced LIGO and advanced Virgo had already been suspended due to COVID-19. So we could not actually make a joint observation yet. But anyway, among them, this binary neutron star merger as an epoch-making event, because they were not only observed by LIGO and Virgo, but also by a number of other detectors or telescopes from gamma ray to radio. So this is the start of the multi-messenger astrophysics. So gravitational wave observation started in 1 minute scale, and then followed by gamma ray, X-ray, ultraviolet, optical, infrared, and radio, up to 10 days or so. And so all of them gives us profound information about the nature of the short gamma ray burst, as well as heavy elements created by this event. And we are now have found that our universe has a number of massive black holes as well as some neutron stars. So this is a picture of the masses of the black hole coalescing to make a heavier one in unit of solar mass. Now, our Kagura, it is a world's first 2.5 generation gravitational wave detector in the sense that it's located in deep underground, 1,000 meters below the mountain, as well as the mirrors are kept cryogenic. Yeah, which gives us, in principle, a very good sensitivity, design sensitivity. But we are now improving the sensitivities, and finally reached to this least requirement in the beginning of this year, as I said. But at that time, LIGO and Virgo were already suspended. So hopefully, in the next observation run, Kagura's sensitivity will be even more improved, and we can detect real signature of the gravitational waves. In my institute, we are planning to install a new computer cluster to detect and analyze the signal. Now, as for the scientific aspects, the new big mystery revealed by advanced LIGO and Virgo is the fact that our universe have a lot of black holes, massive black holes, much heavier than the sun, like 20 solar mass, 40 solar mass, or even 60 solar masses. And they are very difficult to explain by the gravitational collapse of normal stars, because they lose masses by stellar wind before collapsing. So this is a typical figure of the effect of the stellar wind. So no matter how large the initial mass of the stars, like 100 solar mass or even 200 solar mass, as long as we take the standard solar wind mass loss, the final black hole mass is at most 13 solar mass or 14 solar mass. So we cannot explain massive bodies in terms of normal stars. So two candidates remains. One is the first generation stars with low metallicity, which do not suffer from mass loss, or primordial black holes created just after the Big Bang. And this question, namely, which is the real origin of these massive black holes, may be answered by the multi-frequency gravitational wave astrophysics, which I have been advocating for more than a decade. And one possible way is to launch a space-based laser interferometer like BDESIGO This is a planned project in Japan and probes a frequency range of 1 Hz or even 0.1 Hz. And if they are put into practice, they can detect the events of the 30 solar mass black hole merger up to the redshift around z equals 30, which corresponds to the very distant universe or early universe when the universe size was just 1/30 of the current size. And at such a distance or at such a distant past, there were no stars because first stars were created around 10 to z equal 10. So if we decide to find such an event at a distance universe, this is nothing but of primordial origin. But it takes time to build such a space-based detectors. So more practical way to probe primordial black hole is to focus on their formation process. So these primordial black holes are created when large density perturbation enters the horizon, cosmological horizon called Hubble horizon, and its mass is around the horizon mass at the time of creation. For example, to create a 1 solar mass black hole, the creation must have taken place t equals 10 to minus 5 seconds after the Big Bang. And this is not the only story, but this high density perturbation also creates a gravitational waves, and whose typical frequency is also related to the mass of the black hole, like this. Here, this is a primordial black hole mass. So again, for a solar mass black hole, we would find a stochastic background of gravitational waves in the frequency of about 10 to minus 8 Hertz, or the wavelength of 10 light year or something like that. That was shown in my one of previous paper. So this figure represents that there is one-to-one correspondence between mass of the black hole and frequency of gravitational waves. And the abundance of these primordial black holes is related to the energy density of the gravitational waves. And there are a number of constraints. Ground-based detectors cannot probe such a small energy of gravitational wave. But as I said, space-based detectors can do that. And pulsar is also used to probe, because timing residual noises of millisecond pulsars can probe the long wave gravitational waves with their period nearly observation time. And now we have about 10 years of the observation accumulation. So we can probe up to 10 light year wavelengths of the gravitational waves. And as observation time gets longer and longer, so higher mass scale black hole can also be probed. But very recently, interestingly, one of the collaboration of the pulsar timing constraint group called NanoGrav collaboration reported possible positive detection in their 12.5-year data. But this is above their 11-year constraint, so care must be used to interpret their result. But anyway, here in this frequency region, they are more or less noises. But there is some hint that actual signals may be present. And by fitting this kind of power law, we can guess the typical amplitude and power index. And these colored lines represent a possible interpretation of this graph. And some people have already argued that this may be the smoking gun of the fact that solar mass primordial black hole were created, and NanoGrav has already discovered the signal of associated gravitational waves. But I think we need more care to interpret them, because this 12.5-year data is somewhat above the other constraints. So anyway, the multi-frequency gravitational wave astrophysics. So LIGO found massive black holes, and this may be probed by pulsar timing as well. So combined with these three possible means of observations, we can find more and more interesting news in the future. So please pay attention and keep tuned to this new era of the gravitational wave science. I stop here. Thank you very much.
Good evening. Hi, I'm Lizbeth Tan. I'm here to present my SPP paper with Sir Ian Vega. So, here's a quick overview of my presentation. So, let's start with what is a tidal disruption event or a TDE. So, a TDE occurs when a star passes by a black hole, causing it to get disrupted. The disrupted material gets accreted onto the black hole. Uh, and this makes the black hole produce light. So the light comes from two sources. So first, when the material accretes onto the black hole, it heats up, producing a flare. Next, sometimes uh, material are ejected at the poles of the black hole, which produces jets. So when we observe events from Earth, we get light curves or light profiles. So here's an example. So the light profile is a plot of the luminosity versus time. And when the star is fully disrupted, we get a t to the negative 5/3 power law for the luminosity. So uh, TDE research are usually done with numerical simulations. One of the earliest works was published in 1989. So in their paper, they showed that the shape of the star changes uh, as it orbits through the around the black hole. A more recent example is this paper in 2013. So they did hydrodynamical simulations to show how how increasing impact parameter disrupts the star. However, numerical simulations are computationally expensive. So for our work, we opted for analytical methods. So uh, here we model our star as a polytrope, which follows the equation of state given by this pressure and density relation. K is just a constant, and gamma is an index. Uh, with this, we can use the Lane-Emden equation given by equation 2 to get the density profiles of our stars. So theta is the density, while c is the radius, and n we denote as the polytropic index. And gamma and n are related by this expression. So the Lane-Emden equation has analytic solutions, but only for three indices, for 0, 1, and 5. So we plot them here in this figure, and the first root of the solution indicates the radius of the star. The rest of the indices can be solved numerically. But we want analytic solutions for all indices from 0 to 5. So we use approximate analytic solutions. So here we have an example of the numerical solution compared with our approximate solution for n equals 4.5. So we use two approximation, one near the center of the star and one near the surface of the star, and we connect them with the line. So our first approximation is the usual Taylor series expansion. Here we assume the solution to be of this form. Then we plug this in the Lane-Emden equation to get this solution. And next, we use Horde's approximate solution. It has this form. So C sub 1 is the first root. Theta sub 1 prime and eta are given by these relations, and C sub ij are just constants. This form is still a bit difficult to use for analytical calculations, so we just consider the first two leading order terms as indicated by equation 9. Now we have our density profiles for the star. Next, we discuss our TDE toy model by Lodato King Pringle. So the Lane-Emden solutions are plugged in here. So after a change of variables, you get rho hat. Then we can solve for the mass distribution for different radii x. Then we can solve for the mass distribution for given energies epsilon. With this, we can now get the accretion rate in equation 11. In this model, we assume that the light curve observed is proportional to the amount of mass accreted onto the black hole. So here we compare the dm by d epsilon plots for the numerical and approximate solutions. You can see that our approximations follow the general shape of the numerical solutions, and we have limit our indices to n equals 3 because the higher indices give curves that are qualitatively different from their numerical counterparts. When we have dm by d epsilon, we can get the accretion rate or the light curve. So the approximate expression is given by equation 14. Here, f, g, h, and j are pure functions of n. And we can see from this expression that the leading order term gives us the canonical t to the negative 5/3 fall off for full disruptions. Now, we compare this approximation again with numerical solutions. Here, lower index stars are less centrally concentrated than higher index stars, so they are easily disrupted. That's why they have a steeper rise at early times, and they also approach the fall off faster uh, at late times. Uh, Recall that we've modeled our density profile in the middle as a line. So we expect that our middle approximation for the light curve does not follow the numerical solutions. So to summarize, the numerical solutions shows us only the overall shape of the curves, but an analytic solution can give us the independence of the light curve. As I have said, lower index stars are more easily disrupted since they are less centrally concentrated. And last, the leading order term of our approximation gives us the canonical t to the negative 5/3 fall off at late times. So, thank you.
I am Marco Galino from the Gravity Group of NIP UP Diliman. On behalf of my advisor and co-author, Dr. Ian Vega, I'll be presenting our work entitled Steady-State Density Perturbations Induced by a Point Mass in a Finite Cylinder. Now, the outline of my talk starts with an introduction of dynamical friction, which sets the main context of this calculation. And I will proceed with the methods used in the calculation and the results obtained from such calculations. And I will end my presentation with some remarks and prospects for future work. So first, what is dynamical friction? Dynamical friction, simply stated, is the momentum loss experienced by a moving object as it interacts with a gravitationally induced wake. Now, to better illustrate this, let us look at this video, this visualization, which shows the perturbations that is induced by a moving object along some orbit. Now you can see that there is a formation of density trails which depend on the speed of the object. Now we were able to calculate or obtain an analytic expression for the density perturbations in different speed regimes, which are dependent on the value of the Mach number, which is the ratio between the velocity of the object or the speed of the object and that of the speed of sound in the fluid. You can see in the diagrams on the right that the density trails are much pronounced than in the subsonic regime. And there is a formation of other structures in the supersonic regime, which tells us that the effect or the force that is exerted on these perturbers will be different, or these objects will be different depending on the speed. Now, this was calculated previously by Kim and Kim in 2007, where they calculated for the radial and azimuthal components of the dynamical friction force exerted by these perturbations on the moving object. Hence, we can actually summarize the whole dynamical friction problem into two steps. One that is looking at the density perturbations induced by a moving object, and that of the force that is exerted by these density perturbations on the object. Now, in this SPP paper, we focused on the first step, but the additional extension of this problem will be on backgrounds that are finite. Now, in real astrophysical systems like a protoplanetary disk, the background medium wherein an object is evolving is actually finite. Much like in this optical image, actually an edge-on image of a protoplanetary disk in the Orion Nebula, where there is a distinct boundary between the disk and that of the surrounding medium. Now, this begs the question, from a theoretical point of view, what could be the effect of the boundary on the perturbations? And since we already established that there are two parts in this problem, the perturbations will then affect the dynamical friction that is experienced by the evolving object. Now, to answer this problem, we considered a first approximation. So we looked at a circular orbit that is immersed in a finite cylindrical disk with dimensions 2L, which for its length, and radius capital R. And this circular orbit is defined by its radius R0, angular speed omega, and mass m, which then leads us to a definition of the Mach number to be equal to omega R0 over the speed of sound, cs. Now, I emphasize this Mach number parameter since most of the analysis for late-time dynamical friction is dependent on the Mach number. Now, to solve for the density perturbations, we have to solve for the Euler fluid equations simultaneously. And to obtain the perturbations, we linearize these equations to obtain a wave equation, which tells us how these perturbations propagate through space. Now, this wave equation is sourced by a Dirac delta function, at least for our case, in order to look at the effect of a point particle mass that is evolving through time. Now, it is this point particle is modeled using a Dirac delta function, And to solve this, what we did was to do an expansion, a basis function expansion of the Dirac delta function, which enabled us to um, obtain a solution of this form, where R is the radial piece of the solution, and the angular and the actual pieces were expressed in terms of sines and cosines. Substituting this to our equation, we obtain this differential equation for the what do you call this, for the function R mn. This equation is actually a Bessel differential equation, but the solution to this depends on the sign of alpha mn, of the square root of alpha mn squared. Now, the solution Rmn satisfies the following boundary conditions. Here, we assume that the walls of the cylinder is reflecting. Therefore, we assume that we imposed a Dirichlet boundary condition at the wall. We also imposed that the solution is regular at the origin, and that the solution is continuous at the orbital radius, but has a jump discontinuous derivative due to the fact that we are considering a system wherein the source is a Dirac delta function. For the results, we first look at the boundary matching. Of course, we have to ensure that the solution is indeed continuous and that the derivatives are discontinuous at the boundary, which is at R naught. So we can, we are sure from this illustration that the function is continuous and that it approaches zero at the wall, which is at this point. Another observation that we can see here is the formation of negative densities, which are actually under densities. So if we compare our result from before, in which the background is infinite in spatial extent, the primary feature in these density plots are the formation of density trails, whereas in this case, introducing Dirichlet boundary conditions or reflecting boundary conditions for a specific case, wherein the radius and the length L is equal to 2 and R naught is equal to 1. There are these density trails do not appear, and there are regions wherein there are under densities, which then would significantly affect the calculation for the dynamical friction. So what have we done so far in this calculation? We obtained an analytic solution for the density perturbations in a cylindrical disk. But the solution is limited to subsonic to transonic regimes. We found out that the solution becomes poorly convergent in the supersonic regime, wherein M is greater than 1, the Mach number is greater than 1. And lastly, the existence of reflecting boundaries then induce the formation of under densities. So after this, what can we do? We can introduce other boundary conditions, maybe time changing. We can also consider double perturbers, a star and a satellite planet. And of course, we should use the density perturbation solution that we obtained from this calculation to calculate for the dynamical friction, which actually is something that I did for my master's thesis. Before I end my presentation, I would like to acknowledge the support of the Office of the Chancellor of UP Diliman through UP OVCRD, project numbers 2020-02, TNSE, and 1937 ORG. Here are my references. Thank you very much.
A good day to everyone. I'm Jana May Angeles, here to talk on cosmological dynamics in a self-tuning cubic Horndeski theory. So why dynamics in this theory? Well, despite the success of the lambda CDM model in predicting cosmological observations, which suggests general relativity as the most viable theory of gravity at the moment, the current mysterious nature of the dark components in our universe warrants a study of alternative theories in gravity. The simplest of such theories is the scalar tensor theory, where some scalar field is coupled with gravity, and the most general scalar tensor theories that gives rise to second-order fluid equations are called Horndeski theories. In this discussion, we focus on the cubic sector of Horndeski, a subclass of Horndeski theories that is sometimes also called kinetic gravity braiding. This choice is motivated from the fact that this subclass satisfies the constraint that gravitational waves must travel at light speed or luminally propagate in spacetime, passing a kind of screening mechanism that filters out non-viable theories. In particular, we study here a cubic Horndeski theory, which admits a self-tuning solution that gives rise to this action with the following relations and variables. Self-tuning is a scenario where cosmic acceleration is independent of the bare cosmological constant lambda. This aspect of the theory enables it to bypass the discrepancy between the observed and theoretical values of the cosmological constant, as we can screen up a large bare lambda into a small effective one. Now it has been hypothesized that the cosmological dynamics of this theory should approach the scenario where the scalar current J vanishes. Though the J is a conserved current that arises due to shift symmetry. In the paper, we investigate this hypothesis using the dynamical systems approach to gain insights, particularly in the late-time regime, the Z dynamics, as we want a solution with late-time cosmic acceleration and vanishing J. In building our model, first we assume that our universe is flat, homogeneous, and isotropic, characterized by this Friedmann-Robertson-Walker metric, with a uniform scalar field component that is co-moving with the background and another component that acts like a perfect fluid with rho and p denoting its energy density and pressure respectively. Then, the action in equation 1 leads to this dynamical system that represents a two-dimensional phase space with state variables J and H. Note that H is the rate of the universe's expansion, and W, the equation of state parameter, relates the energy density with the pressure of the perfect fluid. So, a point in the phase space represents an initial condition of J and H, and trajectories within the phase space are solutions to this system. By equating our dynamical system to zero, we obtain the following fixed points. A fixed point is simply a feature in phase space where trajectories that start from this point remain on it for all time, and it can be characterized by the nature, specifically the sign of their corresponding eigenvalues, which gives us an idea on how trajectories behave around this point. We can graphically see the different behaviors of the trajectories around these points that we obtain when we look at the phase portrait of the system. Before we do so, it would be good to bring into attention the stable fixed point, as this basically means a self-tuning scenario. Here we show the phase portrait of the given dynamical system for sample values of W, specifically when the universe is filled with baryonic matter or radiation. Both phase portraits share similar features, so we can just focus on one. We notice the saddle located here that attracts some trajectories and repulses them into another direction. We also notice the stable fixed point here that attracts nearby trajectories and the unstable one here that repulses them. One interesting solution that we see is a period of contraction followed by an accelerated expansion, which can be a topic for future work. Now from these plots, we can infer that in general, for the case of positive H, or for an expanded universe, a universe with a non-zero value for J will eventually evolve towards an end state where J becomes zero. This supports the hypothesis that the cosmological dynamics of this theory should approach the scenario of a vanishing scalar current. Not only that, this end state also implies a scenario where cosmic acceleration is independent of the bare cosmological constant. We say in general because there are exceptions, like the trajectories proposed by the saddle and do not have the stable fixed point as their end state. Also, and this is probably not clear in the plots, but the red curve, which we will call hc of j, is a discontinuous region in the phase space, since our system, specifically h dot, blows up at that curve. So we are not sure how trajectories behave in this curve. So for completeness in our analysis, we resolve this dilemma by applying a change of variables restricted on the curve. Thus, j dot and h dot becomes phi dot and h, where the curve is no longer discontinuous. So hc of j is now parameterized as hc of phi dot, and we obtain the following one-dimensional dynamical system on the curve. If we equate this to 0, then we obtain the fixed point phi dot equals 0, which coincides with the stable fixed point in the original system. As this is always negative, then trajectories on this curve would move towards the fixed point. Thus, we now know that trajectories on the red curve behave like other nearby trajectories in the original system. To conclude our discussion, we showed that the cosmological dynamics, the self-tuning cubic Horndeski theory, has cosmic acceleration with vanishing current as an attractor, which can support the given hypothesis. We could use a numerical black hole solution and solar system constraints to further restrict this theory. Perhaps the restrictions might remove the trajectories that are exceptions of the hypothesis from the relevant solutions to the theory. For another future work, we can also check out the perturbations of the theory and see how it affects its cosmological dynamics. Here are the list of the references in this presentation. Thank you for listening.
My submission for SPP with Dr. Ian Vega, entitled Black Hole in Spirals in an Expanding Universe. I am from the Gravity Group in the Theoretical Physics Group in UP Diliman. My talk is divided mainly into three parts. First, I will talk about what motivated this research, which is basically on source modeling of gravitational wave sources called black hole binaries under astrophysical environments. Next, I will talk about our chosen environment, which is an external cosmic pull by an expanding universe. Then lastly, I will talk about how this factor will affect the gravitational wave-induced orbital evolution. Okay, firstly, this work, as I said earlier, is motivated by a surging interest on accounting astrophysical environments around black hole binaries and isolating their effects on observables like the one shown here, like the shifts in the pericenter of the orbit and the gravitational wave phase. This because so far, current source modeling popularly used by LIGO and future detectors for template generation and data analysis only considers isolated sources in a vacuum. Here are some of the relevant astrophysical environments in gravitational wave astronomy compiled in this paper by Barause et al. As you have heard earlier, a talk by Mr. Ugalino, which he talked about dynamical friction. For our work, we have chosen to study black hole binaries under cosmological effects, specifically an expanding universe. Besides the reason that it is currently accepted that the universe is expanding under a rate related to the Hubble constant, as stated by, as said by Jana earlier. This also an interesting theory problem, since we are now considering black hole binaries in non-asymptotically flat spacetimes. We note that the current work on on quantifying these effects have not yet considered gravitational wave-induced orbital evolution, or the radiation reaction, which should be important since emission of gravitational waves will affect the orbital trajectories, which is itself the source of the emission. Okay, we note that we consider our system as a compact object orbiting around a non-rotating black hole, which is described by the Schwarzschild metric under a de Sitter spacetime, which describes a universe under a constant acceleration of expansion. This is called the Schwarzschild de Sitter spacetime, or the Cutler spacetime, and is a solution of the Einstein field equations with a positive cosmological constant lambda. Okay, we now describe the dynamics of orbits under this space-time. First, we consider that Schwarzschild de Sitter, or SDS, bound orbits can be described as ellipses under this trajectory equation, similar to a Keplerian solution for the orbital trajectory. We have the following geometrical parameters: P or A, which is the semilatus rectum, or the semi-major axis of an ellipse, describes the orbital size. The eccentricity E, which is greater than 0 or less than 1, which describes the degree of ellipticity of the bound orbit. And also the angle swept, which is psi, the angle swept by the orbiter around the central object. We also note here RA and RP, called the APO, or the peribaratron, which is the minimal and maximal distance of a bound orbit around a black hole, which will be used for obtaining the energy and angular momentum of a bound orbit. We show here the derived shifts in the conserved quantities due to lambda, wherein the negative signs denotes generally lower requirements to keep the orbit bound. We also derived a shift in Kepler's third law, which is the period or the angular velocity to orbital size relationship, which also has a negative sign, denoting a generally lower angular velocity due to the cosmological constant. We now examine how the orbit would evolve under dissipation of energy and angular momentum due to emission of gravitational waves. Using the gravitational wave energy and angular momentum fluxes derived by Hawke and Agarwal, as well as Bonga and Hasbun a few years ago, we obtain, using a coordinate transformation, the evolution of the orbital parameters, P and E, wherein the dot denotes a derivative with respect to time. We only keep here the standard literature results plus the leading order dominant lambda effects. We also note here that these are the orbital evolution equations averaged secularly over a complete cycle. Okay, so some notes on the orbital evolution equations. We see here that we cannot describe the evolution of circular orbits, and the equations are only limited in the elliptical parameter space. This is emphasized by the appearance of a diverging 1 over E factor in the cosmological term, which tells us that as the orbit decreases its eccentricity, the orbital evolution will increase further its P and E, since they are coupled. Also, this is only valid in the post-Newtonian and post-de Sitter sense, or the large P and small lambda approximation, which in turn will only describe the early inspiral phase of the black hole binary coalescence, or the weak gravitational field limit. Finally, the negative sign of the cosmological terms denotes faster decay of the orbit and will scale for a higher cosmological constant. Okay, using a relatively large cosmological constant compared to the experimentally measured lambda, we show here some of the orbital trajectories under gravitational wave-induced evolution, which is obtained from solving the orbital equations numerically and using the elliptical trajectory equation shown earlier. We show here the orbit of a compact object around the central black hole in the XY orbital plane, with the blue line as the leading post-Newtonian literature result of gravitational wave-induced orbital evolution, versus the red line, which is our result, accounting for the leading order lambda effect on this same orbital evolution. Oh, sorry. So we see here that at early times, it shows a minimal effect on the orbital evolution. However, as we see that at longer times, the radiation accumulates, and we see here that the orbit lags in its angular velocity. But we see here a notable faster decrease in the orbital size. For a smaller initial orbital size, we see here that there's a point that the angular velocity becomes faster due to both the lambda and the greater accumulation of radiation emitted, and also we see a notable faster decrease in the eccentricity of the orbit. Okay, we conclude from the results shown earlier that the cosmological constant has several effects on a black hole binary. It lowers the requirement for bound energy and angular momentum, leading to a higher decay rate due also to a higher flux. And there is also some notable deviations in the orbital trajectories, like the effect on the angular velocity shown in the orbital plots earlier. Lastly, we note here that although we have used a far more hypothetical value for the cosmological constant as compared to the actual current experimental measurement, the lambda here can serve as a stand-in variable for the magnitude of any other gravitational environment that could affect a black hole binaries with the potential scaling as 1 over r squared. And this could include either a Roche potential or quadrupolar fields like a magnetic field. So we acknowledge in this work the help from these institutions, the OVCRD grant and the DOST scholarship.